So there's a point I really want to drive home in this video, and that is that you always get your angle from the graph. And so I've got a good example here to explain this. So in this case, the angle is 5 pi divided by 4, starting at the polar, and we're working in the polar coordinate system. So starting at this axis, and you trace out, and that angle is 5 pi divided by 4. And so we're asked to graph z equals -1, -i, and this will correspond to the points -1, -1, which is shown here. And really the trick to this, so you remember in the last video we were working with SOHCAHTOA and Pythagoras theorem, and the issue with this situation is, using SOHCAHTOA, if we just worked with so tan theta equals opposite over adjacent, which would be y divided by x, and we took the tan inverse to get the angle of y over x, then we would have actually gotten an incorrect angle, so -1 over -1, which would have given the angle of pi divided by 4, which is clearly wrong because we can see from the graph that the actual angle is 5 pi divided by 4. So in this case, using trigonometry, it would have said the angle is just right here, but that's not the case. And so it's very important when you do work with imaginary and real parts of complex numbers and graphing it, that you do actually graph it, and just make sure that your angle checks out. So of course, and we can figure out r still. R, it's just, did in the last video, r squared x squared plus y squared. So this is our x, this is our y. So r, or the modulus, is equal to 2, or in this case we're dealing with so -1 squared plus -1 squared, which is there we go, -1 squared, which is the root of 2. So r is just the square root of 2. And so it's very important. The values of theta should always be found from the diagram rather than the formula, even though sometimes this will work out, but mainly if you're just dealing in the first quadrant. And the other thing to note is that actually this has an infinite amount of angles here, because when you think about the unit circle, if you travel around once, that's 2 pi. And so really we could represent theta as 5 pi divided by 4, or it could be 5 pi divided by 4 plus 2 pi. Or it could be, the common way that it's written is theta equals 5 pi divided by 4 plus 2n theta. Where really n is just any integer, so it could be 0, it could be 1, it could be 2, it could be, I don't know, it could be 100. It doesn't matter. There's an infinite amount of ways you could describe this angle here. So this is, in mathematical terminology, how we do it. And the other thing to note is that, this is a great conversion here. So this situation, this is good for the Cartesian coordinate system. But when we start moving to the polar coordinate system, we begin using, this way. And you can just transfer between these two. This is good for polar. And even better, so this is really what you're going to want to start working in a lot. So for polar, we like to represent it this way. And so how would we represent, -1, -I in this form? Well, let's just go through all of them. So in this case, z would be x is -1 and minus I. And then another way we could say it is r, which is square root of 2 times cosine of 5 pi divided by 4 plus 2 n pi plus I sine 5 pi divided by 4, hopefully you can see this at 5 there, plus 2n pi. And then finally, to put it in this form, we would have the square root of 2, which is the radius, times e to the I, 5 pi divided by 4, plus 2n pi. And really all this is doing here is just accounting for all the possible angles that we could include. And just one final note is sometimes you'll see, r can be written a few different ways. So r is also the same as the modulus of z, which is also written as mod z. And whichever way you see it, it is just equal to x squared plus y squared from Pythagoras' theorem. All right, thank you. Have an excellent day.